there.
Good morning, all of you. So today I welcome all of you to the 16th Siksha Anusandhan weekly academic lecture organized by the Center for Applied Mathematics and Computing. Today we have with us Dr. Gopal Rayaguru as our speaker, and he will be delivering his talk on the topic Horadam symbol elements. So Dr. Gopal Rayaguru is currently working as an assistant professor in the Center for Applied Mathematics and Computing, ITER, Siksha Anusandhan deemed to be university since June 2021. He has done his BSc in Computer Science from Khalikot University, MSc in Mathematics from Sambalpur University, and PhD from NIT Rourkela. He has qualified GATE with All India rank 108 in 2015. His research interest lies in the field of number theory. He has 19 publications in journals of national and international repute like Turkish Journal of Mathematics, Mathematical Communications, Integers, the Fibonacci Quarterly, Journal of Indian Mathematical Society, Ball de Sociedad Met Mexicana, etc. Research collaboration in India as well as countries like USA, Romania, Colombia, and Turkey. He works as a reviewer of the American Mathematical Society and Gentleblatt Math. He has also attended various national and international conferences and workshops. So I would like to especially thank Dr. Gopal for preparing this lecture in less than 2 days because our scheduled speaker unfortunately fell ill. So anyway, thank you, Gopal. So now I would request you to start your talk.
Okay, thank you for the invitation, ma'am. Let me share my screen. Actually, I also get less time, so I could not prepare properly. Let me share actually. Can you see the slide, ma'am?
Yes, slide is visible.
Okay, so let me start. So today I'm going to discuss about some Horadam symbol elements. So the main two things to be discussed here is the Horadam numbers, and the second one is the symbol elements. So this is my outline. So I will start with the introducing Horadam numbers and quaternions, octonions, then symbol algebra, and then next Horadam symbol element and some of the properties. So Horadam numbers are actually binary recurrence sequences. I mean the sequence Horadam sequence is a binary recurrence sequence which is defined by this wk plus 1 is equal to p times wk plus q times wk minus 1 with the initial terms as w net as a naught and w1 as a1. So here this a0, a1, p and q, all of these four are arbitrary means integers, okay, and we can say these are the parameters which define this Horadam sequence. And the condition for this Horadam sequence is the discriminant means for this recurrence pwk plus qwk minus 1, the discriminant p square plus 4q that must be positive. That is the means minimum requirement for this Horadam sequence. And corresponding to this recurrence relation of this Horadam sequence, we can have the characteristic equation x square minus px minus qx is equal to 0. And upon solving, if you are having, we will have two real roots like alpha is equal to p plus square root of p square plus 4q upon 2, and beta is equal to p minus square root of p square plus 4q upon 2. So these two real roots of the characteristic equation corresponding to this Horadam sequence consider means they generate a closed form expression for obtaining the kth term of this sequence. So this is the formula that each kth term of this Horadam sequence Wk can be obtained by this fraction, where the numerator is capital A times alpha raised to the power k minus capital B times beta raised to the power k, and the denominator is alpha minus beta, and this capital A and capital B, they are solved by means of this I mean substituting the initial values W0 as A0 and W1 is A1. So we will get capital A as A1 minus A0 times of beta and capital B as A1 minus A0 of alpha. So this is the closed form expression for the Horadam numbers. So this is about Horadam numbers. So before going to the symbol elements, I would like to say about Fibonacci and Lucas numbers. So this Fibonacci and Lucas numbers, we can say these two sequences are particular sequences of Horadam sequence where these parameters are fixed. So we are fixing the parameters in Fibonacci sequence as A0 as 0, that means initial condition A0 as 0, A1 is 1, and the values of P and Q as 1 and 1, both P equal to Q equal to 1. So that gives the Fibonacci sequence, and in case of the Lucas sequence, both P and Q are 1, but the initial values are A0 is equal to 2 and A1 equal to 1. So this Fibonacci and Lucas sequence are particular cases of this Horadam sequence. And if we'll go to the recurrence, then that will look in this form: fk plus 1 equal to fk plus fk minus k, fk minus 1, and lk plus 1 equal to lk plus lk minus 1. So we can have the binary formula like this. And for the Lucas numbers lk, if we will write the binary formula, then that will look like lk is equal to 1 plus root 5 upon 2 raised to the power k plus 1 minus root 5 upon 2 raised to the power k. So this is all about a slight introduction to Fibonacci and Lucas numbers, because basically I am going to use the Horadam numbers in the symbol elements. So before going to the symbol elements, or to know what is symbol algebra actually, I would like to introduce what is quaternion. So as like complex numbers are ordered pairs of real numbers, that means we can say that complex numbers are a two-dimensional, means generating a two-dimensional space over the reals, because complex numbers can be viewed as ordered pair of two real numbers. So basically we are constructing a two-dimensional space over the reals. So quaternion can be further means we can say that quaternions are means extension or the generalization to complex number. So on the field of complex number, we are constructing another two-dimensional space. Okay, so this was first discovered by Hamilton in 1843, and he applied this mechanics of this quaternion to three-dimensional spaces, and it also comes in use in various applications that will I will say. But I would like to say that the thing was, see, whenever we are extending the pairs, so either from real to complex, or from any two-dimensional space or three-dimensional space to four-dimensional space, like that, that pair-wise addition and pair-wise subtraction is quite easy. But what if we want to multiply? Like in complex number, when we multiply, we are having the root I, so that I square is equal to -1. So that I plays a crucial role in the multiplication of complex number. So that is the main thing. Pairwise addition and pairwise subtraction is fine. But when we want to suppose divide, or when we want to multiply two numbers in the complex system, or in the further extension if you are doing to any dimensional space, that is the main issue. So that means solving that problem by Hamilton solved actually that problem. Rather, he was actually extending from complex number to a three-dimensional space, but he obtained quaternion. That is actually means we can view that as a four-dimensional space. So quaternions are usually represented like this: a plus b times of I plus c times of j plus d times of k, where this I, j, and k Okay, this I, J, and K are basic quaternions. Okay, and the multiplication over this quaternions is defined by like this.
Dr. Sai, 1 minute, 1 minute. Just, Acha, is this quaternion group? They form a group. Is that
Uh,
quaternion you are talking about? IJK.
yes, yes, yes. So
Okay, okay,
not from the group of that the actually that
fine.
goes in some different direction. Means
Hmm.
like torsion group you are saying. Actually, it is not going
Hmm.
in that direction. It is something
Acha, acha.
means
Okay.
we can say there is a Kelle Dixon construction means defined by A Kelle and Ellie Dixon. They means they found a
Hmm.
rule that generating a two-dimensional space over any prior space. So
Acha.
there means we have to define certain unique multiplication property so that it will make different from the previous one. So here the multiplication rules are defined by this: I square is equal to j square equal to k square is
That
equal to
that
ij
this.
k minus 1.
Yes, sir.
Like in complex number, we are simply doing I square is equal to minus 1. So this I is the means primitive root of 2 of 4, we can say. So because I raised to the power 4 is only equal to 1. Other than that, the fourth roots of unity are both plus minus 1 and I and minus I. So this I and minus I are actually primitive roots. So this primitive root actually plays a crucial role. So the multiplication in quaternions is actually non-commutative. Up to complex number, commutativity is there, but when we come to quaternion, that commutativity property is lost. Further, this quaternion can be extended to octonions, where again means in quaternion we have the associativity property. Associativity property holds in quaternions, but when we extend this further to octonions, then that associativity property also lost. So in modern mathematical language, we can say that quaternions are a four-dimensional associative normed division algebra over the reals. So here, since means associativity norm division algebra is coming, so I would like to say what is means division algebra and associativity. All we know the associativity property. So let's come to division algebra. So formally, we start with a non-zero algebra D. Basically, algebra means a structure with some algebraic property, so that we call as algebra. So reals, we can say the field of reals, that is an algebra. We can say the field of complex, that is also an algebra. So algebra is basically a structure we are constructing with certain elements with some fixed properties, algebraic properties. So formally, if we start with a non-zero algebra D over any field, then we call that D is a division algebra if for any element in D, we can have two elements like x and y, for which means A equal to bx. Okay. So for any element, any non-zero element B in D, there exists precisely exactly one x. Okay, precisely one element x for which A equal to bx, and similarly exactly one element y for which A equal to yb. So, and when you come to associative algebra, associativity property holds. So that is ax equal to xa equal to 1. Like in the division algebra, we are writing a equal to bx and a equal to yb. So this x and y are different. When this x and y are equal, then at that time we can say that this division algebra is a associative division algebra. So there is a theorem by Frobenius which states that up to isomorphism, there are only three associative division algebra. That is the dimension 1, that is for the field of reals, then in dimension 2 for the complex, and dimension 4 for the quaternion. That's what I was saying, that when we extend these quaternions to octonions, this associativity property is lost. So we can say means any finite real finite dimensional division algebra over the reals must be isomorphic to R or C if unitary and commutative, if both of these property holds, and equivalently the associativity property. And this commutativity part is lost in case of the quaternions. So except this commutativity property, if any real finite dimensional division algebra is existing of the degree I will say 4, then that is isomorphic to the quaternions. And similarly, if we means exclude both of these properties, means associativity and commutativity, then the real finite dimensional algebra, division algebra of the I will say dimension 8, then that will be means isomorphic to octonions. Okay, because we are leaving this associativity part and commutativity part. And here is a term I have written, that octonions are non-associative but alternative. So alternative is something a property like associativity but not exactly associativity, like when we product suppose x, y and z. So in associativity what we do, x and in the parenthesis y into z is equal to in the parenthesis x into y and then z. Okay, so but in our octonion, both of the means we will write means we will denote that x into in the parenthesis yz is equal to xy into z, and there is another property like that, both of them hold, but actually what we say that equality that is actually lost. So that property is called actually alternative. And after this octonion we can further extend to sedenions and like that. So it the dimension goes in 2 to the power n. So in reals it is dimension 1, then complex dimension 2, then in quaternion dimension is 4, octonion dimension is 8, in sedenion the dimension is 2 to the power 4, that is 16, and so on. But after this octonion, up to this octonions, means there does not exist any non-trivial zero divisors. But when we extend from octonions to sedenion onwards, in sedenion and also in the further extension, there exist zero divisors. So when zero divisors exist, then dealing with that algebraic system becomes difficult. So usually the study means goes up to octonion, means basically most of the researchers means who do research in these areas, they do operations up to octonions, and from the sedenion onwards, the I will say the work is going on, means to determine how many non-trivial zero divisors exist in a sedenion, a particular sedenion. Why I am saying particular? Because the multiplicativity property we are defining, that is not unique. Yes, we can say that if we are defining two octonions, let's say suppose, then those two octonions are isomorphic, but the multiplicative rule we will define, that is means more in number, perhaps 480 or something, might be in the next slide. So quaternions are used not only in pure mathematics, but it also have practical uses in applied mathematics, like particularly in the calculation involving the three-dimensional rotations, such as three-dimensional computer graphics or computer vision, crystallographic texture, and etc. And they can also be used means to replace the means methods, predefined methods of rotations, Euler angles, and like that. So this can, means if sufficient work is done, then this can be alternative to the predefined methods. Those are used in these rotations or computer visions or graphics like that. So as I told, that octonions are again two-dimensional extension over the quaternions. So there in octonions we were having x is equal to x naught e naught. So instead of e naught I wrote 1, because I wrote a plus bi plus cj plus dk, and both all I, j and k are fourth roots of unity. So here in octonions, x can be means represented in this form, x naught e naught plus x1 e1 up to x7 e7, and these xi's are all reals. Okay, because we are taking the real numbers and simply we are extending the dimension. So here xi's are all reals, and this one of the means multiplicative property defined I defined here is EI, sorry, I left here. Actually, this is not EI equal to EJ. This is EI product with EJ is equal to EI when this EJ equal to 0, or EI into EJ equal to EJ when this EI equal to 0. And for the rest of the cases, okay, so this product EI EJ equal to EI or EJ depending on these two cases. If EJ is 0, then this product is EI, and if EI is 0, then this product is EJ. And except these two, the other means otherwise we can define this EI EJ is equal to minus delta Ij plus epsilon Ijk times of Ek, where this delta Ij is nothing but the Kronecker delta function, and obviously Kronecker delta function. So whenever I is equal to j, then the value is 1, otherwise it is 0. And this epsilon Ijk is a completely antisymmetric tensor with the value 1, but for some values of Ijk, like when we particularly take Ijk equal to 123 or 145, 176, 246, 257, 347 and 365, only for this 1, 2, 3, 4, 5, 6, 7, only for these 7 Ijk pairs, if we are taking epsilon Ijk is equal to 1, then this property along with this property EIJ with this product, that makes this a octonion. Okay, so actually this definition or this I told na that multiplicative rule we are defining, that is not actually unique. There are as such 479 more possible definitions for this octonion, and here I have used that E not equal to 1. Here I have used E not equal to 1. Like in case of quaternions, the first means value product with A was 1. So here also I have taken E not equal to 1. So out of 480 possible definitions, this is the one definition. So such more 479 possible cases are there, means that can be defined, or that multiplication rule can be separately defined to means produce a octonion algebra. So if we are dealing with some octonion algebra, then we have to particularly look for the means product rule what is defined. Accordingly, we have to compute the means whenever we are computing the product of two means elements in that octonion algebra, then we have to follow the rule accordingly. Means whatever the rule is defined, accordingly we have to compute. It is not like that we have defined and someone don't know the product rule what is defined and he will compute, then the answer will be something different, and that will lead to some absurd cases. So obviously means with the permutation of these values of E1, E2 up to E7, because I have taken E not equal to 1, so taking E not equal to 1 and permuting these 7 means elements, or we can say the roots E1, E2 up to E7, 480 different algebras over means this means 480 different octonion algebras can be defined, although they all of them are means isomorphic. So next come to symbol algebra. I will say this symbol algebra is completely different from this extension like quaternion to octonion, octonion to sedenion, because there we are generating the two-dimensional space. So it goes like in 2 to the power n manner. So the dimension goes in 2 to the power n manner. But in symbol algebra, the symbol algebra is different. However, the symbol algebra of degree 2, in symbol algebra we always have a degree of n, and when symbol algebra is of degree 2, that particular algebra is the same as the quaternion algebra. But after quaternion, this symbol algebra part is separate extension, and this octonion or sedenion, this Cayley-Dickson construction is separate extension. So symbol algebra is means different from the extensions like octonion. From quaternion to octonion, that extension is completely different in case of symbol algebra. So in symbol algebra, I will say means let means so many things to be considered at a time. Let n be a positive integer, let n be any positive integer, and k is a field for which that characteristic of k is not divisible by n. or sorry, the characteristic of k that is not that will not divide n. If that is the case, and n is containing means if omega is some nth root of unity, and particularly the primitive nth root of unity, that means omega raised to the power n is equal to 1, and before that if we are raising that omega to some kth power, that k is less than n, then that will not be equal to n. So omega is the primitive nth root of unity, and the characteristic of the field is not dividing the considered positive integer n. Then after that, if we denote k star is equal to k minus 0, that means all the non-zero elements of the field k, then for any a and b, or any particular a and b from that k star, we will define any algebra S over that k with this rule, that x raised to the power n is equal to a, y raised to the power n is equal to b. Okay, we generate the algebra S with the algebra over k generated by two elements x and y, so that x raised to the power n equal to a, y raised to the power n equal to b, and yx is equal to omega xy. So here also comes the non-commutativity property, because yx is equal to omega times of xy. So with this, if we construct the algebra S, then we call this S as symbol algebra and of degree n, because we considered nth root of unity omega, and we used that omega in this definition, that, and actually we took two elements x and y and defined this rule, means we bound this algebraic structure S by this rule, that is x raised to the power n is a, y raised to the power n is b, and the product yx is equal to omega times of xy. So this algebra is called symbol algebra. So when we can say when n is 2, you can see x square is a and y square is b, and yx is equal to w xy. So w we are considering, since n is 2, so yx is equal to minus of xy. So this rule means coincide with the quaternion means rule, the multiplicative rule defined in the quaternion, that coincide in the symbol algebra with the degree 2. So the symbol algebra is degree 2 is called the quaternion algebra. So they coincide. So for each symbol algebra defined over this field k, we have a k basis. Okay, so we have a k basis. Now in 1963, Horadam defined the nth Fibonacci quaternion and nth Lucas quaternion, actually both. So where he replaced this because the general definition is what, quaternion, the nth quaternion is equal to, or sorry, the quaternion an element, any element in quaternion is of the form a plus I times of b plus j times of c plus k times of d. So replacing those a b c d by means of consecutive Fibonacci numbers, that is fn, fn plus 1, fn plus 2, and fn plus 3, he denoted this element, as he started from fn, he denoted this element as the nth element of this Fibonacci quaternion. And the rules are same, I square and j square k square is equal to minus 1. And as I told that when degree is 2, we are taking the square root of 1. So that is minus 1, that is minus 1 is primitive root. So ij is equal to minus of ji. Okay, and since I into j into k equal to 1 minus 1, we can easily compute that ij is equal to minus of ji is equal to k, and similarly jk is equal to minus kj equal to I, k into I equal to minus I into k equal to j. So this is the multiplicative rule, means the multiplicative rule is fixed from the quaternion. Simply we are replacing that arbitrary ABCD with consecutive 4 Fibonacci numbers, that is fn, fn plus 1, fn plus 2, and fn plus 3. So subsequently many other studies means replacing the Fibonacci number with Lucas sequence, and another recurrence sequences, they are called the Fibonacci Narayana sequence, though I am not I am not telling about Narayana sequence. This is similar means binary recurrence, but in Fibonacci what happens, fn is fn minus 1 plus fn minus 2, but in Narayana sequence there is a gap. Okay, so this is also related to means one can search for the cow saddle problem or something like that, or we can simply search for this Fibonacci Narayana pattern, and that is related to a problem as like rabbit problem. So replacing this Fibonacci sequence by any other recurrence sequence means and various so many authors studied subsequently, means many studies have been done means studying these properties, finding their norms, and also the same in case of the octonian algebra and so on, replacing means these terms. So next I come to symbol elements. So what happened in Flout and Sevin Flout and Sevin in one paper I have not cited, and after that again Flout Sevin and with another third author consider the symbol algebra of degree 2. Up to 2 it is up to quaternion algebra, so this coincide. So next is degree 3. They studied for degree 3 symbol elements and with the Fibonacci and Lucas number. So they defined Fn is equal to Fn into 1, Fn plus 1 into x, Fn plus 2 into x square, and so on up to Fn plus 8 into x square, y square. So I will go here again because I told here that S means symbol algebra has a k basis. A symbol algebra over k has a k basis of the form x raised to the power I with y raised to the power j, and where both of these I and j varies from 0 to n minus 1. 0 to n minus 1, these powers vary. So accordingly we will put that x raised to the power 0, y raised to the power 0, then x raised to the power 1, y raised to the power 0, and so on. If we will do, then in the means the basis contains how many elements, means we are considering n number of elements, so starting from 0 to n minus 1 into, so there are in total 9 number of means basis. Okay, so not basis actually means in a basis there are 9 number of elements, or we can say a tuple with 9 elements. So he defined means they defined Fn is equal to Fn plus 1, Fn plus 1 into x, like that up to Fn plus 8 into x square, y square, and the same in case of Lucas number just by replacing this Fn and Ln. And one should not confuse with this. In Horadam, in Fibonacci quaternion, this capital Fn is denoting the nth Fibonacci number, and in symbol element this capital Fn is denoting the Fibonacci symbol element, but one should not confused with the notation because they are different. Simply the notations are same, but it is different. Here this small fn and small nn actually denotes the nth Fibonacci and nth Lucas numbers respectively. Okay, so there are several studies again means replacing this Fibonacci and Lucas number in the symbol element of degree 2, degree 3. Further studies have been done and their behaviors have been studied, because for the first time actually Flout 7 and the third author studied this degree 3 symbol algebra with this considering these recurrence terms. So they studied their behavior, and they searched for some applications of this number. And the special numbers I wrote, that is means we can say same as the Horadam numbers, but with certain restrictions. With certain restriction, the Horadam numbers. So they denoted them as special numbers, and accordingly they used those numbers, and they told that a special quaternion, special symbol elements, and all up to degree 3. So our objective, or my objective, is to generalize this concept of Fibonacci and symbol elements to Horadam symbol elements, not only in degree 3 but also to any degree n. So I consider this symbol algebra S in general of degree n generated by x and y over the field K. So S has a K basis, as I told, of the form x raised to the power I, y raised to the power j, where both I and j lies from 0 to n minus 1. Okay, it runs over 0 to n minus 1. So we can have a basis like this. Okay, so if we denote the ith term of this set or of this basis, if I'll say this is a basis, and if I will denote the ith term as e I minus 1, because I am starting from 1. So if I denote the ith term as e I minus 1, so I can write this like this form E naught E1 up to En square minus 1. But if someone is means changing the order of the basis elements, then the further computation, again as I told, it will depend on the basis. Means we have to be very conscious while considering the basis, and what is the notation we are using for the ith term of the basis. So we have to be very conscious when we are doing the computation. We have to keep in mind the defined basis and the operations. So if I denote, means if I fix this basis as E naught E1 up to En square minus 1, so there are in total n square number of elements in the basis. So this is an ordered basis. Why I told ordered basis? Because I am not going to change the order. If order is changed, then behavior of the elements will also be changed. So with this ordered basis, we define the kth term of the Horadam symbol element like this: Wk, capital Wk is equal to L varying from 0 to n square minus 1, small wk plus L with El, where this El is the lth element of this order basis I consider, and Wk plus L is the k plus lth Horadam number. Okay, the thing is similar as let me scroll up. So as here in Fibonacci symbol element, we are means simply writing fn plus 1, fn plus 2, and so on, fn plus 8, and we are multiplicating the basis elements correspondingly. The similar thing is here, but it is in dimension n. So this capital Wk denotes our kth Horadam symbol elements. Okay, so as I told that tuple wise addition and tuple wise subtraction is the same, means whatever the dimension you are extending, like means this is simply a linear algebra concept, that when we are extending to any dimension, then the addition and subtraction means is done means point wise, coordinate wise. So for this means Horadam symbol element we define. So here also we check that this Horadam symbol element we defined, it also satisfies the same recurrence as that of the Horadam sequence or the Horadam numbers. But there in Horadam sequence, the terms that initial terms W0 and W1 was like A0 and A1, some arbitrary one real number. But here the W0 and W1 are means n square tuples. Each tuple contains n square number of elements. So we can say W0, W1. So this inside means inside the tuple, this W0, W1 up to Wn minus n square minus 1 is written. So each W represents the particular Horadam number, or the means we are if you will say Wk, then that small Wk is the kth term of the Horadam sequence. Okay, so this is our capital W0 and W1. With this capital W0 and capital W1, the same recurrence holds for the Horadam symbol elements also. And since recurrence relation is holding, we can have the characteristic equation like this: lambda square minus p lambda minus q is equal to 0, for which the roots are obviously alpha and beta, same as the roots of the characteristic equation corresponding to Horadam numbers, because both of the recurrence are same. So obviously characteristic equation are same and the roots are real roots of those characteristic equation are same. But here, why I have denoted this alpha underbar like this summation and beta underbar like this summation, because actually we are finding means we are finding the closed form expression. We are trying to means as like Horadam sequence, since the same recurrence relation is holding, whether similar properties of Horadam numbers or Horadam sequence is being satisfied by the Horadam symbol elements or not, that is our one of the motto. So means we consider the kth element of the Horadam symbol elements, we express them in this usual form that we considered. Then since our small wk plus l is the k plus lth Horadam sequence number, we replace the binary form in this place. Then with means adjusting this summation, or means taking this a alpha raised to the power k to the outside of this summation, and beta raised to the power k to the outside of the summation, we will arrive at this A alpha k upon A alpha minus beta, and summation varying from L equal to 0 to n square minus 1 alpha raised to the power L EL, and the same with beta, and here is a negative sign in between. So this summation again and again, writing this summation in this form is quite difficult. So we have we have put a notation for this. So this summation L from 0 to n square minus 1 alpha L EL is alpha underscore, okay, and the same for beta H beta underscore. So with this notation, we can see that the kth Horadam symbol element can be represented of this form, which is not exactly means we will say binary formula, because in binary formula roots of the characteristic equation are involved, and this A and B are solved by means of the initial condition. But here with this we are having alpha underscore and beta underscore, which represent again this summation with the what element means lth element of the order pair. Okay, so this is something we can say binary like formula, okay, or any closed form expression that means resembles something not resembling actually, but similar to a binary formula for Horadam numbers. And we also saw that these the Horadam symbol elements satisfy many more similar properties as like of the means Horadam sequence that I have not means included in this slide, but definitely I will show. Next is means here we are actually the second motto is to find the zero divisors. Okay, so here zero divisors exist. So under the condition that letting wk with these usual parameters a0, a1, p and q, okay, the Horadam sequence, considering the same Horadam sequence I denoted as 4.1 the equation. So and this is the usual definition, a0, a1, pq, they are integers with discriminant positive. So with these Horadam numbers, if we consider that GCD of P, this coefficient P of WK, and A1, that means the second initial term W1 as A1. If this P and A1 are having GCD more than 1, okay, and let R be any prime positive integer such that this R divides this GCD of P and A1, okay, let the finite field FB is equal to ZR, okay, because we have considered that R is a prime, so ZR is a finite field. So over this finite field, okay, if we extend further, then let's say K is equal to ZR of epsilon, okay, and let AB belongs to this K star, that is non-zero elements of K, and epsilon be the primitive root of order 3, because we were in the symbol algebra definition, we were extending the means we are considering the primitive nth root of unity, since but here we have considered the only degree 3, so the third primitive root of unity. So if that is some epsilon, then extending this finite field over this epsilon, that will be some K, and from that field extension the non-zero elements of K is considered as K star, and we will take some elements A and B, okay. So we will say S is equal to AB upon this K and epsilon. This whole total with this property will be a symbol algebra of degree 3, and we take that they are generated by the elements x and y. So obviously this is the property x cube is equal to a, y cube is equal to b, y x equal to epsilon xy, and it has a basis, okay. So we consider the reduced norm of the means reduced norm n of this any element of this symbol algebra, okay, and this reduced norm is means this was defined by the by Sabin and Plaut and Sabin in the earlier paper while they studied Fibonacci symbol elements. So that norms look something like this. If Z belongs to the symbol algebra of degree 3 and Z is represented means with this basis that Z is equal to summation running over I and J from 0 to 2 x raised to the power I, y raised to the power j, Cij, okay, this Cij are our constants, okay. So means they computed the Cij's constants, okay, while finding the norm, and they arrived at this, that the reduced norm, this is the smallest norm. Okay, they go on further reducing this computation, and they arrived at this. So we can simply say that is norm of Z over this symbol algebra of degree 3 with this particular basis. Okay, that is of this form: a square times of this means this computation inside the parenthesis plus a times of this, and so on up to this. So this whole total computation will give the norm for this particular element Z of this form. Okay, so in kth Horadam symbol element, okay, since we are considering the symbol element in Horadam numbers, so if Wk represents the kth Horadam symbol elements over the symbol algebra of degree 3, so we will represent like this, that this basis which I considered. Okay, so again I will tell that the computation is completely based upon the basis we are considering. So if we'll consider capital Wk like this, small wk are Horadam numbers. So with the above properties, we can find the zero divisors, okay, and the norms. So this is a proposition. Let Wn denote the nth Horadam symbol element, and lar and r be an odd prime positive integer which is not equal to 3, and r divides the GCD of p and a1. Further, r is not dividing q. Okay, q is the second coefficient in the recurrence. Okay, so and r does not divide a naught, that is the initial term w naught, and epsilon be a primitive root of order 3, okay, of unity. And let the field k is the extension field over the field of means zr, okay, because r is prime is considered. And with the means as the symbol algebra in the definition, we consider certain things, and based upon that we are having an algebraic structure that we call as the symbol algebra. So if with this property we are having a symbol algebra S equal to AB upon K epsilon, we can see R does not divide A naught and R does not divide Q. These two things were not there in the part, and R does not divide A, not divide B. These things were not in the symbol algebra definition. But for finding the means reduced norm of the symbol elements of degree 3, some these conditions are means some more conditions are required that we imposed in this proposition. So with this all of these conditions, we can means take that norm means computation, and we can find that the even indexed Horadam symbol elements will have the norm like this: q raised to the power 3m multiplied with n naught cube, and inside the bracket this many number of terms with multiplication, certain additions. So whole of this means the representation will give the reduced norm for the even indexed Horadam symbol elements. Okay, so the index is 2m here. Okay, so even indexed Horadam symbol element will have this norm. Okay, and the Horadam symbol elements W2m, okay, is a non-trivial zero divisor in the symbol algebra if and only if two conditions holds, that is q raised to the power m is congruent to 1 mod r. Okay, and that is, I can say this q is a means you can say this the property of this modular property. Okay, and also with the with modulus r, a square plus a square b square plus b square plus 4ab plus 1, this value is congruent to 0 mod r. Okay, so if both of the conditions hold, then that W2m or the 2mth Horadam symbol element will be a non-trivial zero divisor in the symbol algebra we consider. And conversely, if this is if we are saying that W2m is a non-trivial zero divisor of that considered symbol algebra, then these two conditions need to be hold. And from this proposition we can have a remark, or we can say a corollary. So that is states that if a Horadam symbol element W2m is a non-trivial zero divisor in the symbol algebra, then this R is congruent to 1 mod R. Okay, sorry, there is a typing mistake actually. This Q is congruent to 1 mod R. Okay, so next proposition, as we found the norm and the zero divisor for the even indexed Horadam symbol element, the second proposition is corresponding to the odd indexed Horadam symbol element, so that it will cover all the Horadam symbol elements, and it will find the all odd and even indexed non-trivial zero divisors in the symbol algebra. So here the conditions are means same. Okay, the above conditions are same, but in case of this odd index Horadam symbol elements, I say this norm is defined like this. Okay, q raised to the power 3 plus 3. Again, we can find the non-trivial zero divisor. Okay, so there the condition is to be a plus b into q is congruent to 0 mod r, or a into b into q raised to the power 6 is congruent to -1 mod r. Okay, out of these two conditions, any one condition at least holds. But in case of this even indexed Horadam symbol element, we have two conditions. Both of the condition needs to be hold for the non-trivial zero divisor condition. Okay, so one can means this is means I will say actually there are lots of reference, so I have not included actually. So you can go through this paper. Okay, this is a joint work with Diana Sevin from Columbia and Professor Panda, and this is the paper. This is published in Notes on Number Theory and Discrete Mathematics. Okay, so you can go through this paper to find the other means references for means the study that is in that paper, and I have not included. But if I let me share this screen. Okay, my PDF of that paper. Okay, there we can see these are all means properties of PQ Fibonacci and PQ Lucas number. That means with condition initial terms as 0, 1 and 2, 1, the same recurrence with P and Q. So see, you can see just have a look at these identities, and I will scroll down to show the identities corresponding to Horadam symbol elements. So just have a look. Okay, so we actually defined the generating function, various summation identities, means weighted summation identities, also alternating summation, like summation identities involving binomials. Okay, they are the properties for Horadam numbers, and one can see the similar properties holds for the Horadam symbol elements. I'm scrolling up quickly, may or may not be visible, but means simply notations are means you can see like some notations are being different, but thing is same, but it requires a lot of computation, means inside computations is required. As I showed, the same or the similar exact property holds in case of Horadam symbol element. And this is one of the case, because we are doing the extension of the basis. Okay, so in case of addition, so those properties they means they follow certain summation rules, so that's why they look means almost equal. But when we come to this product properties, they look means a bit different, but similar. Okay, here as you can see, the generating function is containing alpha under bar, beta under bar, again alpha raised to the power m, yeah, then e e raised to the power alpha k product with s, like that. Okay, so these are some properties. I am simply scrolling down. Okay, those who are interested, they can go through. So, and in the proof of the proposition I told in the last slide, okay, they involve means certain properties those were defined in the previous sections of this paper. That means certain identities means have been defined, that are being used to prove the means to prove the means to prove the result for non-trivial zero divisor condition. Okay, so thank you. uh, if you people have any questions, then you can ask. Hello? Hello? Hello?
Yes. It is audible, audible.
Okay, sir. Thank you. So,
Dr. Sai Gopal,
yes, sir. Thank you.
very nice presentation.
Okay, thank you.
Very nice presentation. Okay. And you explained very well also.
Thank you. Thank you.
So this is completely new to us. Though we have read little bit about the numbers, but tell us, doctor,
Yes, sir.
what are the real field applications? Just tell us one applications where you can use these numbers.
I wrote that it is being used in the computer graphics, and I will say these three-dimensional jobs we are doing. Mostly, these things are used there to create. Means when we are seeing some animated movies or some three-dimensional graphics we are seeing. Okay, so there these things are being used actually. So actually, I have
Actually,
not looked into particular any application of this part, but one can, if someone is interested, then one can go. Actually, this means study over this symbol algebra. I will say this involves a lot of means algebraic structures, algebraic properties, and means computations are means very lengthy. I will say so.
and because I have read somewhere, if you are taking a complex number, two-dimensional, complex number itself is two-dimensional, so that can be taken as a
Yes,
point
yes,
in 2D. Similarly,
yes.
if I take ijk, so it is taken as a point in 3D. Then if you take I, J, K, and L, it is a quaternion, right? And
Yes,
actually,
but
Einstein has
here
given a
primitive roots are means this primitive root of unity plays a crucial role actually.
hmm, actually,
And yes, so
really.
actually they no doubt they are isomorphic, but when we are changing the basis, then that looks something different actually. Means a whole different thing will appear. Means with the algebraic property they
But
are
number,
isomorphic, no doubt, but they look exactly different.
I
Means
must
something.
appreciate you, Dr. Saigopal. I must appreciate you. You have done research in number theory, which is considered to be the very difficult subject to do research.
Okay, thank
Because
you, thank you.
many of the people are doing many things, isn't it? Very difficult to pursue a research in this area. But still, it is a very
Actually, I
nice
will
topic.
say, this symbol elements I have studied and symbol algebra that I considered. Actually, I will say this is this is more towards the algebraic part, not towards the number theory part. Actually, it involves
Exactly.
a lot of algebra.
That is why
Actually,
it is very interesting. That is why I said, because this type of things that you have read in algebra actually.
yes, sir. This is complete means
So
goes
I
into the
cannot say
field of
much.
algebra. Actually.
Yeah, exactly.
Actually,
So nice one.
I
Thank you
use
very much.
means I combine number theory that recurrence with that algebraic system actually or structure. Thank you.
Good one. So anybody, any more questions, please? Dr. Abhijit? Okay, Priyanka, you say?
Very nice presentation, Sai Gopal.
Thank you, ma'am.
You presented it in such clarity that uh, we all enjoyed it.
Okay,
Anyway,
thank you.
many of the persons were having classes, so many could
Okay,
not join, but it was very nice.
okay,
So
thank you, ma'am.
now I think officially, Abhijit, we can end if nobody has any more questions. Dr. Abhijit, are you there? Dr. Abhijit, are you there?
Is it audible, ma'am?
Now I think you were muted or
Yes.
something. We can end it.
Yeah.
We can officially end
So
it.
I shall take a liberty of proposing vote of thanks. Thank we shall thank the speaker, Dr. Sai Gopal Rayaguru, for agreeing to deliver a talk at an urgent basis. So I'm sure that his talk has given us a lot of knowledge on Horadam symbol number, which is a unique topic of number theory and as well as algebra. So that was the talk was self-explanatory and nicely presented by Dr. Sai Gopal. Thank you. Our thanks are due to the colleagues, research scholars, and the students in the audience. Our big thanks goes to Dr. Manoj Ranjan Nayak, the Honorable President of Siksha Anusandhan, deemed to be a university, who have been always a source of inspiration to all of us. I extend our thanks to Professor Sunita Chand, the acting HOD of the Center for Applied Mathematics and Computing, and Professor Manjula Das, the head of the same center, for necessary supports. Lastly, on behalf of Center for Applied Mathematics, Siksha Anusandhan, the university, I extend my heartfelt thanks to all. So thank you once again, Dr. Sai Gopal,
Thank you.
for
Thank you.
presenting such a nice talk. Wonderful talk. Thank you. And thank you all. So hereby I'm officially ending the meeting. Thank you.